Welcome to Deep Dive with Emily and Phil. You wanted to unpack information theory, and I have to say, even I'm curious to see where this goes.
Right.
I mean, we deal with information every day.
Yeah.
But thinking about it mathematically, that's a whole new level.
It really is. It's like taking something we intuitively understand and putting a magnifying glass to it.
Okay.
And what's fascinating is how often our intuition about information turns out to be completely wrong.
Okay. I'm intrigued. Let's dive into these lecture notes we have.
Okay.
I see Professor Wu starts off with this idea that less is more when it comes to information.
Right.
How can that be?
Well, think about two headlines.
Okay.
One says, "Tomorrow the sun will rise." The other screams, "Asteroid to obliterate Earth tomorrow." Which one packs more of an information punch?
Definitely the asteroid one. It's way more surprising, and it completely changes how I see the world. Even if it's hopefully not true.
Exactly.
Yeah.
The less likely something is, the more information it carries. Professor Wu uses this to introduce a fundamental equation, information, represented by I equals the logarithm of 1 divided by the probability of that event happening.
Okay.
Px.
So a tiny probability leads to a huge amount of information because it's so unexpected?
Exactly.
That makes sense.
Oh.
But logarithms. That takes me back to high school math class.
Don't worry. The concept is more important than the calculation itself.
Okay.
Let me give you a more relatable example.
Okay.
Imagine 3 basketball players.
Okay.
Kate, who sinks almost every basket. Matt, who's pretty average, and Alice, who's never even touched a basketball, whose victory would be the most shocking.
Alice, without a doubt. If she somehow won, I'd need to seriously rethink everything I know about basketball.
Right. Her unlikely win carries the most information because it completely overturns our expectations.
Yeah.
And that ties back to the equation. The lower the probability, the higher the information content.
Okay, so we've got this link between surprise and information. But I also noticed something about base values in these notes.
Yeah.
Is that like those different number systems computers use?
It is. Think of base values like different languages for expressing information.
Okay.
We use base 10 every day, but computers use binary, which is base 2, with just ones and zeros.
So like 10 in our decimal system is the same quantity as 10 in binary.
Exactly, just a different way of representing it.
Okay.
And Professor Wu gives an example with coin flips.
Okay.
A fair coin.
Yeah.
50-50 heads or tails conveys 1 bit of information in base 2, but an unfair coin, maybe landing on heads 75% of the time, needs 2 bits to express the outcome. The unfairness itself adds information.
So the base affects how much space we need to store that information.
Yeah.
It's starting to click. But all this is about events that have already happened.
Right.
What of the uncertainty before something happens?
That's where entropy comes in.
Okay.
Think of it like this. You're about to graduate and have no idea what's next. There's a chance of your dream job, a less exciting job, maybe moving back home, or even winning the lottery.
Okay.
We can't know the outcome, only the probabilities of each possibility.
So entropy is a way to quantify that not knowing, that mix of potential outcomes.
Precisely. It measures the average information of all those possible events.
Okay.
Imagine calculating the information content for each outcome using that logarithm equation, then averaging them, weighting each by its probability. That's entropy.
I see. So high probability outcomes contribute less to the overall entropy because they're less surprising.
Exactly. High probability, less information, lower entropy. It's all connected.
Okay.
And there are different types of entropy, like continuous entropy,
Okay.
where instead of distinct categories like job or lottery win, you're dealing with values that can vary continuously, like a person's height.
So entropy is like a gauge of how much chaos or randomness there is in a system.
Yeah.
But how do we compare the entropy of different systems or situations?
Right.
That's where cross-entropy comes in, right?
We got it. Cross-entropy helps us measure the relationship between 2 different probability distributions.
Okay.
Imagine you have one distribution, P, representing the actual probabilities of those post-graduation outcomes.
Okay.
And then you have another distribution, Q, maybe based on your own predictions or a model's assumptions.
So cross-entropy tells us how well Q matches up with P, like how accurate my predictions are compared to the real-world probabilities.
It does. It's basically the average information of distribution Q, but using the probabilities from P. So it's a way to quantify the difference or divergence between those 2 distributions. Okay. Exactly. Think of it this way. If P and Q are identical, their cross-entropy is simply the regular entropy of P. But the more they diverge, the higher the cross-entropy becomes.
So my predictions are way off.
Right.
The cross-entropy would be really high because I'm using the wrong probabilities to understand the real distribution.
That's a great way to think about it.
Okay.
It's just trying to fit a square peg into a round hole.
Okay, so cross-entropy gives us a sense of how off one distribution is from another.
Right.
But what about this Chieh divergence thing I keep seeing in the notes? It seems related.
Yeah, it is.
But even more intense.
It is related. And it builds directly on cross-entropy.
Okay.
Remember how I said that introducing a new distribution Q essentially adds another layer of complexity?
Yeah.
Another source of uncertainty to the original distribution P.
That's like mixing oil and water. They don't really blend smoothly. They just create more chaos.
Exactly. And Chieh divergence measures this excess entropy.
Okay.
It tells us precisely how much additional uncertainty or randomness we've introduced by bringing Q into the picture.
So if Q perfectly matches P, the Chieh divergence would be 0 because there's no extra chaos.
You got it. But if Q is wildly different from P, that Chieh divergence will be large, reflecting the significant discrepancy between those distributions. It's another powerful tool for comparing those probability landscapes.
I see. So both cross-entropy and Chieh divergence help us quantify the difference between distributions, but Chieh divergence specifically focuses on that extra kick of uncertainty that comes from introducing a new distribution.
Precisely. Chieh divergence tells us how much information we're missing by using Q to represent P.
Okay.
It's like trying to describe a masterpiece painting using only primary colors. You're missing all those subtle nuances and details.
Wow, it's a great analogy. So it's not just about the difference between the distributions themselves, but how much that difference matters in terms of capturing the complete picture.
Exactly. It's all about quantifying those discrepancies in a meaningful way.
So we've gone from surprise to chaos, from basketball to masterpieces, all in the name of understanding information.
Right.
I have to say, this deep dive has really opened my eyes to how much we take information for granted.
It's true. We're constantly swimming in a sea of information,
but
rarely stop to think about the underlying currents that shape it. And that's what's so powerful about information theory. It gives us a framework for understanding not just the information itself, but how we perceive it, measure it, and compare it.
It's like we've been speaking prose all our lives.
Yeah.
And suddenly discovered the rules of poetry.
Yeah. I like that analogy.
It's the same language, but with a whole new level of depth and appreciation.
Yeah. And who knows, maybe understanding these concepts will even help us navigate that sea of information more effectively. After all, knowing how to measure uncertainty can be a powerful tool in a world overflowing with it.